we'll discuss the concept of a linear transformation. Well, the definition is you have to have a function that goes between two vector spaces v and w, and in order for it to be a linear transformation, you have to satisfy two properties. One is that f of x plus y is equal to f of x plus f of y, and the second is that f of c times x is equal to c times f of x. Now before we go any further, I want to kind of remind you what subspace test was. Right? We had to check whether or not if you add two vectors it was still in your set, and if you had a constant times a vector it was still in your set. And you hopefully notice there's some similarities there between linear transformations and that's because these two things together are what we mean for something to be linear. Whether it's a linear subspace or a linear function or whatever, this is linear. And so whenever we're talking about linear, these are the two things we want to satisfy. Now again, they vary slightly depending on the context, but here we're talking about linear functions or linear transformations. Now let's look at a few examples. Let's check whether or not each one of these is going to be a linear function. So this first one, it takes in a vector xy, and it spits out a number, and that number is x squared plus y squared, and we want to check whether or not it is linear. So we would check whether these two properties hold. Well, I'm going to tell you that it's not, and the intuition when you're first seeing these is that if you see something that's more than degree 1, it's probably not going to be linear. So degree greater than 1 means it's not linear. But in order to really prove that, we need to find some example where this fails, one of these properties. So here's one example. If I go ahead and plug in 1, 2 to this, I'd get 1 squared plus 2 squared is 5. And if I plug in, say, a multiple of those, let's say 4 times 1, 2, well, that would be f of the vector 4, 8. And if you do this, you get 4 squared plus 8 squared is 16 plus 64 is going to give me 80. However, if I do 4 times f of 1, 2, I get 20, which is not the same as 80. So I showed I have an example where f of c times x is not the same as c times f of x. So therefore, not a linear transformation. And again, if it's not linear, then you need to show a specific case where it doesn't work. And if it is linear, you need to prove that it always works, both conditions. Now this next one is another function that goes from a two-dimensional vector r2 down to a number r. This time it's 2x minus y. And you see we have linear functions there. It makes you think that maybe it is going to be a linear transformation. So let's try to prove that. So I would do f of, so I need to have two vectors added. So let's say, I don't know, x1, y1 plus x2, y2. Well, if you add the vectors together, it'd be x1 plus x2, comma y1 plus y2. And if you apply the function, it's 2 times the x-coordinate minus the y-coordinate. And if I just distribute and rearrange things here, I get this, which is the same as f of x1, y1 plus f of x2, y2. So what this does is it shows you that condition 1 is true for this function. Now we need to check condition 2. So I'm going to do f of some constant times xy. Well, that's the vector cx, cy. And my function says 2 times the x-coordinate minus the y-coordinate. And then notice that I can factor c out of this. And that's c times f of xy. And so once again, it does work. And since both 1 and 2 are true, that means yes, it is a linear transformation. Okay, now let's look at the third one here. This third one is given by R2 to R2, and you take this matrix and you multiply it by the vector xy. I'm going to say it is linear transformation, and so let's go about proving it. Obviously, you might not know ahead of time. Maybe you would try some specific numbers and see how that worked out, but I'm telling you it is going to be. So let's do f of two vectors added. That's f of the new vector x1 plus x2, y1 plus y2. And that's going to be 1, 2, 2, 1 times x1 plus x2, y1 plus y2. And then what I'm actually going to do here is break this up into the x1, y1 plus x2, y2. And then I'm just going to use distributive law here. 1, 2, 2, 1. And we see that this is exactly what we wanted to. This is f of the first vector plus f of the second vector. So it works. And if you were to do the same thing here, f of c times a vector, well, you're going to have matrix times c times the vector. And scalars can always be pulled in front of matrix multiplication. And it's going to satisfy the second condition. So therefore, since both conditions work, that means it is a linear transformation. Last one on here, part D. We have the function f going from polynomial P2 to R by evaluating the function at 1. This is, by the way, called an evaluation map. This one is going to be a linear transformation, and let me show you how this would work. So condition 1, I'm going to add two vectors, and in this vector space, vectors are polynomials. But then, what does this function do? It evaluates the polynomial at 1. So if you plug in 1 into your polynomial, you just get that, which is the same as applying f to the polynomial p, and then separately applying f to the polynomial q, which is what we need for condition 1. And then for condition 2, f of c times p of x would be c times p of 1, which is c times f of p of x. And that works. I will say that sometimes people prefer writing it in the following way when dealing with polynomials. They say something like f of x squared plus bx plus c, and if you plug in 1 to that, you'd get a plus b plus c, and then you can have a1, a2, a1, b1, c1, a2, b2, c2. You could write it out in that fashion, and it works perfectly fine. It just gets more complicated to write it out, but it might be easier to understand what it is you're doing. So it just depends on your preference on things like that, right? You could say something like f of a1x squared plus b1x plus c1 plus a2x squared plus b2x plus c2. If you plug in 1, a1, b1, c1, a2, b2, c2, and then and so on. So there's different ways to handle these polynomials, but using the function notation here, I think that's probably the cleanest way to do those problems. But really, as long as you're getting the work, that's fine by me.